Welcome back to 204D Part 2, and now we're going to discuss the topics that we find in Objectives 4 to 6. First, we're going to look at the basic requirements that we have in order to make sure that we properly control our motor branch circuits. Every motor branch circuit needs three things. We need a means to disconnect it, we need protection from overcurrent, and we need protection from overload. Section 28 inside the codebook gives us all the different rules that we need to know for motor loads. And when it comes to the disconnects, specifically, we need to look at rules 28,600 and 28,602. Rule 28,600 tells us that except as permitted by subrules 2 and 3, a separate disconnecting means shall be provided for each motor branch circuit, each motor starter or controller, and each motor. Subrule 2 says a single disconnecting means shall be permitted to serve more than one of the functions described in Subrule 1. So, for every motor and its associated parts, I need to have a disconnect switch. What that disconnect switch looks like is stated in 28,602. We can use a manual motor disconnect switch for up to 1/3 horsepower motors, but larger than that, we want to use a fuse disconnect switch or an instantaneous breaker. Keep in mind, any disconnect that we use needs to be rated at 115% of the full load current of the motor itself. We also need to have a method of controlling the motor, and depending on what the motor size is, we have a couple of different options. We can use a manual motor control, such as a switch, if this motor is small enough. So the smaller motors can have line voltage pilot devices like thermostats and float switches as well, but they must be properly rated to safely control the motor. They will be rated either by horsepower or by amperage. For larger motor loads, we want to be able to make sure that we can safely turn the motors on and off without exposing the controller to any dangerous levels of voltage or current. So therefore, we can use a contactor for control. In such a case, we would have pilot devices that would initiate the contactor coil instead of the motor directly. So the contactors are only a control device, but they are not a disconnect. Now that we've looked at our disconnect and control means for our motor, we're also going to look at setting up our overcurrent and overload protection requirements. To do this properly, we have to be familiar with what is actually happening inside the motor when we turn it off and when the motor is operating. On the screen, you see two different current charts, one of which you've already seen. The top chart shows us what happens when a motor first starts. When we first energize a motor, what we have is a very high current flow, and that is called the locked rotor current. At this stage, the motor winding is acting like a short circuit because there's no inductive reactance happening yet. Inductive reactance is only going to start to build when the rotor itself inside the motor starts to turn. As that motor starts to turn, the inductive reactance starts to build, which is going to limit my current automatically. But initially, we had that locked rotor current, which is an extremely high current that initiates the turning of the motor. After that motor comes up to speed, then it's going to drop to below the rated current of the motor. The locked rotor current is very important for us to size our overcurrent protection. So our overcurrent protection should be higher than the locked rotor current so there's no nuisance tripping. Whenever we have a short circuit, the current is going to exceed the locked rotor current, so we will still have circuit protection using a higher size breaker or fuse. Now, since my breaker or fuse is sized high enough to avoid the locked rotor current, it's going to be too big to avoid any overloading that might occur. Overloading is when we put too much strain on the motor and we have excessive heat buildup inside the motor itself, which could damage the windings. Looking at the chart on the bottom of the screen, we can see the normal motor operation where we have that initial starting current, and as the motor reaches full speed, we go to slightly below the rated current. But as the motor is being loaded up and used, the current itself inside the motor is going to change, and sometimes it's going to go above the rated current of the motor. If it stays above the rated current of the motor for too long and builds up too much heat on the inside, it could damage the motor windings. So we want to make sure that we protect our motor against this overloaded period. We're not concerned with just small overloads, but we are concerned with more elongated overloads over a longer period of time. The full load current rating of the motor is the highest current the motor can draw consistently without overheating, and it is the rated current that is set by the manufacturer. We want to make sure that we do not exceed that and we do not have too much heat buildup, which is why we have our overloads as well as our overcurrent devices. There's a number of different types of overload devices that we can use. However, most overloads are thermal protection and they will act when the conductor temperature gets too high. Many external overload relays use a small inline heater to warm up a bimetal strip that's on the inside of the overload. We can also have a magnetic overload device that would work on the current and the magnetic field produced by that current. Some smaller motors also will have internally built thermal protection to make sure that the coils don't burn out. All the different overload features that we do have will have a reset button on them. Now that we are familiar with the purpose of our overcurrent and our overload devices and why we need them, we're now going to look at the ampere rating of these. Table 29 is a table that we've looked at before when we started talking about fusing for motors and motor controls. Let's take a little bit closer look at this chart. All of my overcurrent devices need to be sized using table 29. In order to use this table, we need to know what type of motor we're having, if it's AC or DC, if it's single phase or three phase, whether it's a squirrel cage or wound rotor, and what the starter type is. We also need to know what type of overcurrent protection we're going to use. Are we going to use a circuit breaker or do we have a fuse? And is that fuse going to be time delay or non-time delay? The last piece of information we need is the full load current rating from the nameplate. The values on this table are our multipliers. So we take our full load current and we multiply it by the percentage that we see within the column that is associated with our type of motor and our type of overcurrent protection. For example, for a single phase motor, if I were to use a time limit type circuit breaker, I would take the full load current and multiply it by 250% or 2.5. If I had a squirrel cage or synchronous motor and I was going to use a time delay fuse, I'd multiply it by 1.75 or 175%. Motors that have starters usually have a thermal overload relay unit that is included on the starter itself, and it uses small heaters that will respond to the current flow. If we wish to change the overload protection levels, all we need to do is change out the type of heater that we use with it. The maximum rating of a heater is based on the nameplate service factor. The bigger the service factor, the longer an overload condition can safely last. Rule 28306 states that overloads are to be set at 125% of the full load current if the service factor is 1.5 or greater. 115% if the service factor is less than 1.5 or if it is unmarked. So think of the service factor as the durability of the motor. The lower my service factor is, the less durable the motor is. So therefore, we can't handle an overload condition for quite as long. The larger my service factor is, then the more we can allow that overload condition to last, which is where these percentages come in. Remember, service factor is at 1.15 like you see on the screen, then we set our overloads at 125%. However, if it is less than 1.15 or if it is not marked, then we assume the worst and we set it at 115%. When we are sizing the disconnecting means and the control means, we need to look at two different rules within the code book. First, for the disconnect, we have to look at 28602. This states that the disconnect must be rated to be able to open the circuit under locked rotor conditions. So we need to know what that ampacity value of the locked rotor is going to be. And then we need to make sure that that disconnect can handle that disconnecting means during that phase. For the motor control rating, the motor control must be rated to be no less than the motor horsepower rating. So now we also need to know what the horsepower rating of the motor is, whether it is a quarter horse, 3 horse, 10 horse, 20 horse. We need to be able to size my control the same as my motor. 28500 states the conditions of when a motor control is required. Keep in mind, if the motor is small enough, our disconnecting means actually becomes our controller means as well. So if we are going to use a 3-pole switch, for example, on a smaller size motor, then we could use that as our control means. For our contactor means would be used on larger than 1/3 horsepower motors, so we should be aware of the difference between a controller and a starter. You have reached the end of 204D. Return to Blackboard and complete the module review, and make sure you're going over the code rules associated with the motor starter and controller in section 28. Once you're ready, continue on to module 204E.